Hello, I'm gonna tell you about Logistic Mod, which is this device right here. And Logistic Mod is a modulator, so you can use it as a modulation source to map or assign to a parameter in Ableton Live. So it works a bit like CV. And I use an equation to get a value, and then I use that value as the modulation source. So you're seeing that right here. And the equation that I'm using is the logistic equation for population growth. And this is an equation that was used or tried for modeling population growth in animal populations or other purposes. And the thing is that the interesting thing is, and how this relates to chaos theory, is that this equation exhibits chaotic behavior. And if you saw my video for this strange mod device, I talked a bit about strange or chaotic behavior in complex systems. And here I will show you a picture to help demonstrate that for this this population growth equation. So here we can see another way of viewing or going about implementing this equation that we see here. And what we see on the x-axis here is the r value, and on the y we're seeing this equation iterated a certain amount of times. And what we see here is the r value on the x-axis, and on the y-axis we see the x value that goes into the equation. And so So here on the x-axis we see the r value, and on the y-axis we see the result. So at first the equation with a low r value below 3 doesn't exhibit any kind of oscillations. It just outputs a single moving value at a certain slope at any given point in time. And then at some point at 3, when r equals 3, let's see if they have the equation so I can, yeah, it's right here. So here is the equation here, it's very simple. We just have the next iteration equaling r, this coefficient r, the growth rate, and then that's times the x value of the current iteration, so just x, and then this is all multiplied by 1 minus x. So that's the equation. And so when r is above 3, we have a bifurcation, so we have a split in these resulting values, and they're kind of oscillating between these 2 points. So here we have this oscillation, and so I'll take a pause and we'll go back to my device and we'll turn to stepped mode so we can see the true value, and we'll turn the r value, which is right here, down to 1. And let me turn this rate up so it's a bit quicker. Yeah, and we see we just end up with a flat value. And if I turn r up a bit, sorry, too much, we're still at a flat value, because if you'll notice, r is below 3, and below 3 we don't have any split. And as we go above 3, now we start to see the bifurcation. So it's just oscillating between these 2 values. So that's at 3.23. So that's about right here somewhere, just bouncing between those 2 values. And then let's see here, about 3.5, we're at a 4-value oscillation. So let's go there. And there we see a 4-value oscillation. And let's map this now to this instrument. So we have this instrument, some random preset, and I'll map it to the filter. So yeah, we have like a 4-value modulation going on there, step sequence. And then I can slow it down a bit, or actually it's okay. But now let's increase the R value and see what happens. Because, okay, here's what's going to happen. We split into 4, and then 8, and then 12, and at faster and faster rates, until we reach infinity, somewhere around, I can't remember. I can't remember, is it 3.7 something? I don't know, but around this area, we reach infinity and of these bifurcations. And then after that, we have chaotic behavior exhibited. So we have strange chaotic behavior exhibited, just like you'll see in the Lorentz attractor in the strange mod device, or all of those attractors. And so strange behavior, talk about it more there, but it's aperiodic. It's not repeating. It's very complex, but it does have some structure. It has some harmonicity. It has some self-similar patterns. So it looks kind of repeating, but it's a bit different. So let's get to that point in the device so we can understand it and how we'll use this device to get these different patterns. And so right now we're at 4 steps, and then let's speed it up a little bit. And this is just the frame rate of executing the equation. And then let's increase R now till we get something chaotic. At some point we'll get... Actually, I think we're basically there. It went kind of quick. Let me go slower. Yeah, so now we have like a 8-step pattern. Okay, and then we're just gonna go straight on to chaos now. And if I go really fast, you'll really start to see, it has these repeating sequences, kind of, but they're never quite the same. And I'll go to 4, which is the highest we can go. And here we can really see there's these repeating yet chaotic seeming sequences. And so that's what this device offers, some like different ways to have these step sequences that aren't just noise or otherwise. That you can kind of use this to your advantage if it's what you're after. And I give some interpolation modes. So we have a linear interpolation. Oh, before that, on stepped mode, we have a little gliding parameter, so you can kind of glide the steps, which is nice if you want to do a very slow changing step. And then you can have these plateaus, kind of. But anyway, I have a linear interpolation mode and a sinusoidal interpolation mode. And that's basically the device. You can map it to quite a few parameters, and it's not. And otherwise, it's very simple compared to the other devices. But the logistic map really exhibits and was the universality found in chaos theory, and that is this kind of ratio between these these period doublings, which is known as the Feigenbaum constant, and it's about like 4.6 something long, and this constant is a constant. It's found in all these bifurcations, and if you imagine any complex dynamic system, be it in nature or otherwise, they exhibit this same pattern on the way to chaotic or strange behavior. They have this series of bifurcations that get more and more complex until you reach this chaotic behavior, and that could be, happening in maybe many dimensions or something, but this is kind of highlighting the universality, and that basically has chaos theory explaining for these complex behaviors in nature, and saying in the context of that it's deterministic. So instead of saying they're random or they're very specific, especially in a lot of fields that are revolutionized, where maybe these very complex, chaotic behaviors were originally very independently classified, isolated from other behaviors, say in a heart or another complex system. But then along came this universality and chaos theory that explained for a lot of these complex and seemingly random natural behaviors. So that's kind of the historical importance of this equation, and why it's so interesting, and it can be used as a cool modulation source. So I hope you enjoy the device.